All right. So, hopefully you're aware, we got our test in 5 days. I don't know how many days. Thursday to Tuesday. We got our test this coming Tuesday, the 12th, in 1, 2, 3, 4, 5 days. I was right. Good job, me. All right. So 5 days. Now I will post the solutions to the quiz that finished yesterday. I'll post those solutions tomorrow. Reminder that a quiz just opened up yesterday for center of mass and universal gravity. You should do that quiz before the test. I reminded you all that last time as well. Remember, your test is on Tuesday, the 12th, but the quiz for center of mass and gravity isn't due till Wednesday. And you can say, I'll just wait till after the test, but remember the purpose of the quizzes. The purpose of the quiz is to see if you understand it. So if you don't take advantage of that, you may find on the test that you do not understand it. And that's much sadder than if you find that out when taking the quiz. So, at least do one attempt of the quiz on universal gravity and center of mass before the test. Otherwise, you're just kind of shorting yourself. Like, it's up to you. You do you. But that is my recommendation. The quiz's purpose, the reason they exist is just to evaluate, give you a metric of how much you understand. They're not a perfect metric of it. It's only 5 questions. But it's better than nothing. It's 5 questions you haven't seen before, just like the test will be a bunch of questions you haven't seen before. So it gives a better measure than the problem sets in that way. All right. With that in mind, so there's that. Note card, make certain you're here on time. You know, all the usual, don't forget a calculator. I'll remind you all. You all did a really, really good job of that last time. And it may seem like a silly thing, but in the spring, when I didn't send that reminder in all bold, all caps, I had like up to 15 people did not bring a calculator, which is a lot. And it's not, you want to do before you come to my class, you should make sure you have the calculator and you should make certain your calculator works. Like I have extras here, but yeah, man, that calculator is an invaluable tool. If you don't have it, it's very sad for you. You'll have to use one of mine, which, hey, at least you'll have one of mine. But then you have to learn how it works and whatever. If you haven't experienced what it's like to use a calculator that you're not familiar with, it's not a huge deal, but, you know, it just feels weird. You want to give yourself the best chance of success. So, with that in mind, we'll go ahead and jump into making a reminder for myself to get the test ready for y'all. Let's see, joke of the day. Let's see if this one's readable. Oh, there you go. What do you call 2 monkeys that share an Amazon account? Primates. Primates, yeah. Yeah, it's good. All right, your life is improved. Okay, we're going to go through this test to review. This is going to I'll upload this after class. It has some additions to it versus the one that was online. So first, we're just going to do a quick summary of all the things that I've taught you. Oh, and I have my iClicker thing here, so this is going to freak out everyone. There is no we're going to do iClicker questions just because it gives me feedback on what you're doing. These are not graded. Nothing today is worth any points. So, whatever. If y'all see me do an iClicker question, it's not worth any points at the end of the day. It's just so I can get responses. Okay. First thing we covered after the last test was work and kinetic energy. So I told you all about something called work. And I gave you all this equation, and it was intimidating maybe. It was a dot product. You were like, what the heck is that? So work is the integral of force dot dr. And this is then where I told you what a dot product is. A dot product is equivalent. It's a way of multiplying vectors that's equivalent to the magnitude of f times the magnitude of dr times cosine of the angle between them. And I taught you all that the whole point of this dot product is it's just finding the part of f that is parallel. It's finding the part of f that is parallel to dr and multiplying those values. That's what a dot product is doing. You will see dot products again. And if f is a constant, you can see it here. If f is a constant, you get to pull it out. And it just becomes F times D times cosine theta. Woohoo. Hopefully an equation that if hopefully every equation I'm showing you today, you're like, yes, I know how to use this equation. Like, I've used it before. If it's the first time you've seen it and this is looking surprising, that's a very bad sign. Yeah, so great. There's work. I will say a quick aside. I tried to look up where this came from. So remember I told you all of physics, it doesn't come from nothing. It's either an observation of reality or it's derived from something else. This one is really complicated to figure out the history of. Energy is a really complicated history. We started here and all of our energies got derived from this. But in history, probably the opposite was true. They actually found the energies and then they derived work from that, seems to be the narrative. But it's not an easy story, so feel free to check it out. Anyway, we use this to derive kinetic energy. Kinetic energy equals 1/2 mv squared. Close all these notifications so those won't keep popping up. So kinetic energy, if you are moving, you have kinetic energy. That is basically the punchline there. And then, honestly, look, sure, work equals change in kinetic energy, fantastic. Don't really worry about that. This is the bread and butter. Energy initial plus work equals energy final. If you have not been using that at this point, you need to start, that is how you do every energy problem I could possibly give you. What energies do I start with? And there's 3 different ones, and I clearly failed at do not disturbing. Let's try the other one. All right. There are 3 types of energy. One of them is kinetic. So you got kinetic energy. That's a choice. 1/2 mv squared. You have potential energy. And we're going to put that as a U. You have it due to gravity, and you have it due to a spring. Potential energy due to gravity is mg. I am starting to use the letter Y instead of H, because H ends up confusing people. People think of H as how high up you are. I'd much rather use Y moving forward, because Y says, where am I located? And then this reminds us we have to decide where 0 is, and Y can be positive, Y can be negative. So it's the same thing as mgh, but I just think it's more clear. If you use mgh, you're probably more uncomfortable with h being negative. I don't know. Same thing as mgh, but I like it better. Y can be a positive number. Y can be a negative number. It just tells you, hey, where's 0? Am I above that or below that? That's all it's doing. Anyway, these are the 3 types of energies. This is the checklist for any energy problem. Just go through this. Am I moving? Great, I got kinetic. Am I above 0 or below 0? Great, I've got potential. Is there a spring involved? And is it getting squished or compressed? Great, I've got potential energy due to a spring. Anything else goes into work. Any other force that's acting on your problem goes into work. Friction, air resistance, someone pushing or pulling something, that gets chucked into the work term. And the key with work, it's a really, really straightforward thing. Work sounds like a really weird word, but if you can make this correlation in your head, it all makes sense. Work is energy added to system. That's all work is energy added or taken from system. And system sounds like a fancy word, so I'm actually just going to put energy taken or added. If you add energy, your final energy is bigger. If you take away energy, your final energy is lower. That's all work is. Did I gain energy or lose energy due to friction, air resistance, someone pushing or pulling it? If you gained it, work is positive. If you lost it, work is negative. That is all work is. Work is just whether you gained or lost energy. It's a fancy, it's a word that people get, I remember taking this class forever ago, and it was really weird figuring out whether work was positive or negative, because they said work was when the environment does work on the system, it's positive, and work is negative when the system does work on the environment, and I hated those phrases. This is how I understand it now. Did you add energy? Positive. Did you take away energy? Negative. Hopefully very, very straightforward. I hope it makes more sense to you than it did to me way back when. But yeah, this is the bread and butter, y'all. And then, you just need to remember that work. If I said, hey, what's the force involved? You'll find the work. You'll divide by the distance, and that gives you the force. Again, if you haven't done problems with this yet, you're a little behind. You should definitely try doing some of these. Once you've done a few of these, and we'll do one today. Once you've done a few of these, it's all the same process, again and again and again and again. All right, so this slide is just reiterating that energy kind of all goes together. Again, 3 types of energy. The bread and butter is energy initial plus work equals energy final. In your formula sheet, I write it as work equals change in energy. That is how it's written. You will not find anywhere on the formula sheet energy initial plus work equals energy final. But these two things are the exact same thing. If you prefer the one that I've been using, then write that one on your little note card. But these two things that are circled here, work equals change in energy, and energy initial plus work equals energy final, are literally the same thing, just with some algebra done. I just move things around. Change in energy is energy final minus energy initial. Move it over, and you get the same result. So, same exact thing, and it just says, if work is done, I gained energy. If work is positive, I gained energy. If work is negative, I lost energy. That's it. Very, 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 very useful. Energy is a tool, and I can almost guarantee every kind of engineering, you need to know energy. Energy is just a super, super useful tool that lets you calculate problems that otherwise would be very painful to calculate. If you don't, it's like calculus. If you don't know calculus, you can't do certain things. If you don't know energy, you can't do certain problems. I mean, you could do it another way, but man, would it be unpleasant. So, another tool in your toolbox. You got kinematics, you got forces, now you got energy. All right, the unit's joules, everything's joules. Unit for potential energy, joules. Unit for spring potential energy, joules. Unit for kinetic energy, joules. Unit for work, joules. It's all joules. All energy is the same thing, it just changes forms. Again, is energy a real thing? I don't know, but it's a cool thing that if you... just seems to work. Just seems to work. This made-up thing that you can't, measure energy. You can only calculate it. Every single thing for energy here is a calculation. There's no way to, measure energy. Even when you're measuring, the temperature of something, you're saying I'm measuring how much thermal energy. You are just watching how much of liquid rises, and then you're kind of calculating it based on how much it rises and whatever. And then you can get arguments of what can you measure really at all. Whatever. Power is how much energy is output, is how much energy you gain, or how much energy you lose every second to the environment. So the unit for that is watts, and I told you all the most common case that you've probably seen that with is electricity. You'll see that in physics too. How much energy is gained or lost. So in the case of a light bulb, the watts literally means how much electrical energy is converted to something else. It's not all to light. Some of it goes to heat. But most of it goes to light. If it's really efficient, it does a good job. So it's how much energy is converted from one form to the other. Cool. Energy. Good time. Okay. And I'll upload these slides. They're already kind of uploaded, but any extra writing, I'll upload the ones with the writing from today. Momentum is another super, super useful tool that lets you solve problems that otherwise would be absolutely, impossible for you to do. Momentum is a really straightforward thing where, conservation momentum says, as long as all the forces, I can account for all the forces going on inside it, so no external forces, you cannot have gravity acting on things. You cannot have friction acting on things. You can have things run into each other. You can have a car run into another car. That's fine. All the forces are contained within the two cars. You can have a piece of silly putty thrown at the wall. As long as you account for the wall and the silly putty, that's fine. Really, really easy to prove why you can't do it if gravity's there. Momentum is m times v. What's the velocity in this bag right now? 0. Great. So what's its momentum? 0. When I drop it, what's its momentum? Well, while it's falling. Is it 0 anymore? No, look at that. Conservation momentum doesn't work for that. So there you go. There's an easy example for why if there's gravity, you can't use conservation momentum. I say that with a caveat. There is something. So technically, the change in momentum equals the change in impulse. So you can do it, but I haven't given you enough problems with that. So you're not going to see a problem where you're using conservation momentum and kind of sort of, you're not going to see that. Kind of sort of. At least not, yeah. I won't get too much more into that. Anyway, If there's a collision or separation, you're using conservation momentum. That is like, as far as all the problems I ever teach you in this class, this is the most straightforward one to tell you when to use conservation momentum if things collide or separate. Always you're going to use conservation momentum. Like that's almost a guarantee. At least if I say what's the velocities and things like that. So really nice. And then, yeah, you just say sum of momentums in the beginning equals sum of momentums in the end. And there's some examples there. It is a vector. You do have to break it into x and y. We do a problem like that today. When we do a problem like that with two divisions, maybe we're not. But we definitely have lots in the problem set. So, again, we did one in class before. Momentum, very straightforward, but like energy, it's build your own equation. That's the key to these problems. You got to build your own. Add up all your momentums of objects in the beginning equals all the momentums of objects at the end. Remember, there was one really terrible problem where I gave you an elastic collision, the boy and the boulder, and we spent like 10, 15 minutes just doing the math. You will not get a momentum problem where you're spending most of your time on the math. In general, I will never give you a problem on the test where the majority of your time is spent doing math. Assuming and this is assuming you know the physics kind of thing, and assuming you know how to do math. Assuming your competency is equivalent for physics and math, you can expect to spend 60 to 70% of the time doing physics, at most 30-ish% of the time doing math on the problem. Okay? My goal in this test, my goal in general, is not to test you on math. You got plenty of math classes for that. But you do have to do a little bit of math. All right. And there's the impulse thing, which is written at the top here. Great. Oh, the units for momentum, it's just kind of mentioned here. If you don't remember them, just derive them. Really, really easy to derive. P equals mv. What's the unit for mass? Kilogram. What's the unit for velocity? Meters per second. There's the units for momentum. I do not have this unit memorized. I just come up with it in my head whenever I need it. Because it's a weird unit. Kilograms times meters per second. It just comes from multiplying those units together. So don't forget that. Units are important. If you go to someone and say that's a nice cat you have there and they're walking a dog, they're going to be confused. If you don't use the right units, people are going to be confused. You tell someone I have 50 newtons of energy. It's nonsense. It doesn't mean anything. If you don't use the right units, you're not speaking the language correctly. All right, universal gravity. And also to give you all some sense of what the test is going to look like, it's going to be split fair. Each week of content gets about 5 questions. So about 5 questions for work and kinetic energy, about 5 questions for conservation of energy, about 5 questions for momentum, and then it's going to be about 5 questions for universal gravity and center of mass together. Okay? The priority is energy and momentum, but you do need to know universal gravity and center of mass as well. But it is not going to take up as significant. So maybe there'll be 2 or 3 questions about universal gravity, 2 or 3 questions about center mass. All right. Force of gravity. Isaac Newton discovered this. Really cool expression. Describes the force between any 2 objects anywhere in the universe. Done. Like any 2 objects, this is the force they're going to experience as long as they have mass. If you have 2 objects with mass, this is the force they both experience due to each other. There is no assumptions there. There's no requirements there other than they have mass. That's it. Every single one of you is exerting a force due to gravity on every person in this room, every planetary body, every speck of dust, every single thing with mass. This equation works for, which is a really cool thing. This is one of the 4 fundamental forces in the universe, and that's the equation for it, and that's all you need. M1, M2 over R squared, G, the value of that will be given on the test. It is 6.674 times 10 to the minus 11. You will be given that. I do not expect you to have that memorized. And it's got some crazy units to it. The units just make the force work out. So you get newtons, meters squared over kilograms squared. How did I come? I didn't have those units memorized. I literally just picked the units so that if I plug into this equation, it spits out newtons. You can kind of check that for yourself. The meters squared will cancel with the meter squared on the bottom. The kilogram squared cancels with the kilogram squared on top, and you're kicked out in newtons. So the units for this, don't worry about it. You don't need to know those. Yeah?
You cancel one of the masses for the acceleration.
Yes, good question. So the next thing is acceleration due to gravity. And let's just think through an example. The easiest way to explain. So if you look at the acceleration and that equation, let's check the formula sheet. I don't know if I actually gave you the equation for acceleration. It might be one you have to derive if you need it, or write on your note card. Nope, it's not there. And you're like, oh no, how do I get it? The reason it's not in the note card is because it's such a simple step. One of the most important equations I need you to know in this class, biology of the mitochondria is the powerhouse of the cell. In physics, F equals ma. Like F equals ma is like classic. I hope by the end of this class you know that equation like memorized, not because you need to memorize things, but because it's iconic. Like, people say E equals mc squared when they think of physics, but F equals ma is, in my opinion, I don't know. I like it better. Anyway, if F equals that and F equals ma, you just cancel out the m, and the question is which m? Which m do you cancel? You cancel the one that's experiencing the force. F equals ma is the force that an object is experiencing. So m here is the object that's experiencing the force, and the other mass is the one that's causing the force. So if you have to make a decision, which one am I going to use? The easiest thing I can recommend to you, think of the example of Earth. If I want to find the acceleration that you experience on Earth, which mass would I use? I'd use the mass of Earth. If you want to calculate the value of 9.8, you use the thing that's making the acceleration. So the thing causing the acceleration, that's the mass you use. That's the one you use. The one experiencing it gets canceled out. The one experiencing the mass gets canceled out. The one causing the force, you keep that one. And again, the example we did with this one was if you plug in the mass of Earth and you plug in the radius of the Earth, you will find that the acceleration on the Earth's surface is 9.8. The numbers all work out. So this equation, what I do want to remind you all, and this is true of both of these equations, R here is not a radius. So like I just gave an example where it's radius. Sometimes it is. R is the distance between the center of objects. R is the distance from the center of object one. If you have a second object, it's the distance to that object. So if I want to find the force of gravity between the Earth and the Moon, R is not the distance between their surfaces. It is the distance between the center of their masses. We've been using that in a lot of problems. And that can catch you up. If you haven't done any of these problems, it will. Once you do one, you'll find it will catch you at some point. So that's R. If instead I just have the Earth and I want to find the acceleration at some point really far away, the radius in the second example is going to be the distance from the center of the Earth to where that's located. And if you ever want to remember that, easy example. If I say R is the distance to the surface of the Earth, if I go stand on the grass outside, what would be the distance from me to the dirt? Yeah, 0. What happens if you divide by 0? Yeah, undefined. If you take the limit, you get infinite. If I go stand on the grass outside, I don't experience an infinite force. So clearly R cannot be 0. R cannot be the distance to the surface. A very, very handy thing, if you ever want to check your logic, if you ever want to check something, you're like, man, I'm not sure what this goes with. Take an extreme case of it. Take an extreme case of that, and if your logic doesn't work for the extreme case, then it's not correct. So like in this case, force of gravity, 2 extreme cases. We said, hey, we go stand on the grass outside. Does that mean that R is 0? No. That's an extreme case. Another extreme case, what happens when I get infinitely far away? That term goes to 0. That makes sense. If I get infinitely far from the Earth, then I don't experience the Earth anymore. So that's a very, very, very useful tool to check your logic anytime you're trying to decide, am I right or am I wrong? We call those like boundary conditions kind of thing. Look at your boundary conditions. Look at the extremes. If it doesn't work for those, it doesn't work for anything in between. All right. Great. There's that. Then we need to remember that things that orbit go in circles. And any time you hear something is going in a circle, centripetal force to be somewhere, a little light bulb in the back of your head should turn on, back of your mind, and should say centripetal force may be useful. You might not use it, but you should have a little light bulb somewhere in your head that kind of turns on that says, maybe I will. Because, man, if you haven't realized it yet, so many problems that go in a circle use centripetal force. Like, it comes up so much. It's a really, really useful tool. If something's going in a circle, there's a math trick that reveals that all the forces added together equals mv squared over r. Well, if I have two planets orbiting each other, the only force that it's experiencing is gravity. So when things orbit each other, the force of gravity equals the centripetal force, because it's literally the only force acting on it. Things in space, there is no other forces acting on things in space. There's no air resistance. There's no strings attached to things pulling things. There's no normal forces. So things going in orbit, if we assume a circular orbit, mv squared over r equals g m1 m2 over r squared. And you also get the question, this equation is not in the formula sheet. So centripetal force is, but you will not find an equation on your formula sheet that says mv squared over r equals g m1 m2 over r squared. Because that is not a general equation. That's not one that applies to every single situation that you interact with. This is kind of a derived expression for two objects, one object orbiting another. I mean, we've done lots of things going in circles and we didn't use g m1 m2 over r squared. Sometimes with it, whatever. I won't get too much into that. You always have to build the centripetal force equation. That's why you don't find it on the, you don't find mv squared over r equals g m1 m2 over r squared. You don't find in the formula sheet mv squared over r equals the normal force minus the force of gravity. You always have to kind of build that expression. Anywho, but in the case of this, that's the logic. Very, very useful. The masses cancel. What mass is that? It's the one going in a circle. The one going in a circle, that's the mass that cancels. The one experiencing the force. And there's some good problems with that. And then the last equation is the universal gravitational potential energy. There is a very good problem on the problem set that I like. That is, how much energy is required to lift some satellite or something, I forget the name of it, 400 kilometers above the Earth's surface. It's a really good problem, and I really like it because I made a mistake on it, so that makes it more interesting to me. It's not because it's a complex problem. It's because I forgot that R is to the center of the Earth. So I'll just quickly mention this problem. I think it's so as there's something. The problem says how much energy is required to lift an object from the surface of the Earth to a distance 400 kilometers away from the Earth's surface. That's the question. How much energy is required? Go ahead and think about it. You all try to solve it. See if you make the same mistake I did. How much energy is required to lift this thing 400 kilometers? If you've already done the problem, then you'll know the trick. But if you haven't, see if you can think about how you would solve this problem. The key is I'm adding energy to the system. So how much energy is required? If you ever hear the phrase energy initial plus work equals energy final. So then you ask yourself, what is the energy required? That's work. Work is how much energy you need to put in to make this happen. It's not going to happen for free. It's not just going to fly up there on its own. So that's what we're solving for. We're solving for the work. And then the question is, what is my initial energy and what is my final energy? And in this problem, I didn't give it because I should have, but I didn't. I'm going to give you the radius of the Earth. I give you the radius of the Earth, and I give you the mass of the Earth. And I give you the mass of this object as well. You need that. So you get mass of Earth. So how much energy is required? See if y'all can figure it out. Set up the expression. All right. So maybe you have an idea in your head. We'll see if it's right. So what energy do I initially have? And this is where I made a mistake. When I was solving this problem, I made the mistake when I was helping someone with it. I said, what energy is required? And I said, how much energy do I have to begin with? And I said 0. And that's wrong. How much energy do I have in the beginning is not 0. If you say the energy beginning is 0, this term only goes to 0 at a very specific spot. When does the potential energy go to 0? Well, it's not at the center. It's a good guess, though. Infinitely far away. When does this go to 0? There's only one value of r that makes this 0. It's when r is infinity. When I'm infinitely far away from this object, this term goes to 0. Because if you plug in 0 at the bottom here, you get infinite. You get an infinite energy, not a 0 energy. So, long story short, how much energy do I have to begin with? I have the mass of the Earth times the mass of the object divided by the radius of the Earth. That's how much energy I start with. Right now, every single one of you has some amount of energy, like, based on this equation, some amount of energy. And it's not 0 based on this equation. So that's plus work equals the energy final will be the exact same expression. Move this a little bit more because in the forever. All right, equals negative g m Earth m1 over the radius of the Earth plus 400 E3. Yeah, still not enough room. That is inconvenient. All right. Radius of Earth plus 400 times 10 to the 3 because you got to convert to meters and that's it. All right. So try out this problem for yourself. See if you make the same mistake as me. Again, it's just more of a don't make the mistake that this R is the surface, is how far away you are from the surface, because it is not. It is not how far you are from the surface. And if I make a mistake, that means, if it's easy for me to make that mistake, it's easy for anyone to make that mistake kind of thing. Not because I'm anything better, but I've just been doing this for a while, and so usually means it's less likely for me to make a mistake, but not always. So the negative comes from the derivation. And remember, y'all, gravitational potential energy gets larger the farther away you get from an object. What is the largest value that this equation can equal? What is the largest value that negative g times m1 times m2 over r can equal? The largest number. It's 0. What's the largest value this can reach? It's 0. Every other number is smaller than that. Negative 1 is smaller than that. Negative 2 is smaller than that. Negative 3 is smaller than that. Negative 5 is smaller than that. So when is this value the largest? When I'm infinitely far away from it. What's its value when I'm infinitely far away? 0. So the negative matches that logic. Yeah, they're completely different equations. At the end of the day, though, it still obeys the logic that the farther away you get, the larger your gravitational potential gets. And so if we made a graph of this, you'd see that this is the plot of it. And it gets larger, but because it approaches here. All right. Center of mass. Very, very useful thing to calculate. Tells you if I have a bunch of objects, I can pretend like I can condense all of them to a single point. And as far as projectile motion is concerned, I only care about that single point. Super, super useful. Rotation, you do care about how your mass is distributed in a different way, so we'll get to that when we get to that. Center of mass is 1 over all the mass times the sum of where each mass is times its mass. And then we found if you had a continuous object, you integrate. And that integral, the dm, turns into rho dx if it's a one-dimensional object. I really like, you all had a cool recitation activity. I say cool, maybe you didn't think it was cool. You all had a problem during your all's discussion where it was an object that had kind of a shape that was weird. And it said, find the center mass of this object. What was really cool is that you actually, instead of using the density, you used the y as a function of x. And that was the same as a density function. So what's cool with this expression is how kind of tall your object is analogous to your density. If your object's real, like if a part of your object, look at this first chunk of the object, I've got more mass in this little green strip here than I do in this blue strip down here. So it's kind of analogous to density. Density is how much my mass do I have at that location. So I'm not going to ask a problem like that in the test, so don't stress too much. But it is a cool, like, you may be like, when am I going to encounter an object with a varying density that I have the function to? I don't know. But you will probably encounter objects that have varying shapes. And it turns out a varying shape is analogous to a varying density, which is cool. So, fun things. I should have included problems like that in the problem set next year, right? But good news is, if I didn't have you practice it, I'm not going to test you on it. And rule of thumb, I do not look at the recitation activities when developing tests. So, you also got that in your back pocket. All right. Don't worry, we'll practice this. We won't practice this bottom equation, but we will practice the top one. And yeah, the next thing we're going to do, so great, that's it. That's everything I covered. That's my summary. The next thing we're going to practice is I'm going to give you a few examples. And one of the best ways to study for a test is just looking at a problem and determining what topic, what tool am I going to use to solve this. If you can look at a problem and say that's a conservation of energy problem, or that's a kinematics problem, or that's a momentum problem, you are basically 90%, not 90%, you're like 70% of the way there. If you can look at a problem and tell what type of problem it is, the chance of you solving it correctly is very high. So that's like a super, super useful skill. Can you immediately kind of say, step 3, I'm going to use this equation? So we're going to just practice that with a bit. And remember, I gave you all that mixed problem set so you can practice that yourself as well. Again, these clickers are not worth any points today. This is just feedback from me. This is just a way to respond where I can see what you're answering and how people are viewing it and all that kind of jazz. So don't stress it. Not that the clicker questions are ever stressful. All right, an asteroid blows up into 3 pieces. I gave you the initial velocity of the asteroid and the final velocity of the 2 pieces. And the mass of the asteroid and... That's really weird. I gave you the initial velocity of the asteroid, the final velocity of the 2 pieces, and the mass of the asteroid and 2 of the pieces. Find the velocity of the 3rd piece. Is this a energy problem, momentum problem, universal gravity problem, or a center of mass problem? Without any numbers, without any more details, what type of problem is this? And once you identify what type of problem it is, see if you can build the equation with variables. Make up your own variables. All right, close this out in 5, 4, 3, 2, 1. Again, it's not worth any points, so whatever. All right. If ever something starts together and breaks up into pieces, it's momentum. That's guaranteed. And look, I mentioned a bunch of masses and velocities. That's another indication that momentum is a thing that's going to happen. So what would this look like? This would look like the total mass of everything, the mass of the asteroid, times its initial velocity. That's the only object to begin with, equals the mass of the first piece times its final velocity, plus the mass of the second piece times its final velocity, plus the mass of the third piece times its final velocity. And you very likely would have the pleasure of doing this in X and Y. And there you go. There's problems like this. If you haven't seen one like it, there's one in the problem set. Next one. Saturn has a moon, Titan, which orbits it. I get the time for 1 revolution of Titan, and I get the distance of Titan from the center of Saturn. How would you find the mass of Saturn? Is this a conservation of energy, momentum, universal gravity, or a center mass problem? If you're unsure, draw a picture. All right, we'll close this out in 3, 2, 1. All right, so we draw a pretty picture of this. There's Saturn, there's Titan. What path is it making? A circle. And that's kind of the thing that gives the magic sauce. So then, great, it's a circle. I want you all to build the equation for it. Have fun. How would you solve this? Try to build the equation purely with variables. I give you R, and I give you capital T, the time for one revolution. Build the equation. So it's going in a circle. So you got mv squared over r equals the gravitational. What's the only force acting on it? And these are the same r. I'll leave that as little r. So boom, boom. What happens to the mass? Now, you have to ask yourself, which mass does cancel? Does Saturn's mass cancel or Titan's? Titan's, which is great because you can't solve the problem for Saturn's if that cancels. So there you go. So you get v squared over, one of these r's cancels too. Let's make our life a little easier. So you get v squared equals gm2 over r. And then you say to yourself, but I don't have velocity. How do you find velocity? I'll give you 10 seconds to think about it. So much time, right? So if something's going in a circle, we know that its velocity, it's called tangential velocity. How far is one circle? Divided by the time for one circle. Distance divided by time, you chuck that in there. So you get 2 pi r over t squared equals gm2 over r. You rearrange things for the mass. So you get the mass of Saturn equals... And I'm going to do it over here to the side because I have more room. Mass of Saturn equals 2 pi r squared over t. G goes on the bottom. We get another r on top. Forgot to square the 2 pi. 4 pi squared r cubed. Over t squared. Boop. So, if you're a physics major, this is the equation. As you get farther along in your classes, these are the expressions. We stop working with numbers as physics majors. You generate general solutions. In general solutions are better because I can now solve this with any problem. I can find the mass of any object given these values. And I don't have to do any extra algebra or anything. In engineering, in computer science, in like a bunch of fields, generalizability is really useful. So when you're writing a program, you define variables. You say x equals this, y equals this, and then you write your function in terms of those variables. And the beauty of that, when you write your function in terms of variables, you can change the variable values to whatever you want, and you don't have to rewrite the entire code every time. If you're doing engineering and you're doing CAD modeling, when you define the size of an object, you don't want to say the size is 10 centimeters. You say the size is the height, and you set a parameter to that, and then you can change that parameter to whoever you want, and it'll update your model. Fusion 360 is really, really cool for that. If you parameterize your model, if you make it parametric, it's awesome because you can change it and it automatically updates the entire thing. Whatever. General is better. One day you'll believe me. All right. I toss a 1 kilogram ball off a 10-meter high ledge with a velocity of 8 meters per second at an angle of 20 degrees. How high is the ball when it's going 10 meters per second? Is this an energy problem, a momentum problem, a universal gravity problem, or a center of mass problem? Yeah. Oh, yeah. Yeah, let me hit the clicker to see what y'all say. Thank you. It is good to see what y'all respond with. Notice that kinematics isn't a choice here. Yes, you can do kinematics, but that's a lot of work. Energy lets us solve this problem in a single line. And I gave it away, but whatever. All right, it's energy. That's disappointing. All right, great. I told you it's energy. Build the equation. Energy is so cool because it lets you do things so much easier. Man, if you can use energy, you always should. Like, it's so easy. It's not vectors. It's just so useful and so nice. Yeah, I mean, I'll close this out again. It's worth 0 points, so whatever. So remember, bread and butter, y'all, energy initial plus work equals energy final. And you just ask yourself, what energy do I start with? Am I moving in the beginning? Yep, I got kinetic energy, 1/2 mv initial squared. Am I above ground in the beginning? Yep, so mgy, initial. Is there a spring involved? No spring. Is there any work being done by air resistance, friction, someone pushing it, literally anything other than these three? No work done in this problem. Great, work is 0. I'll just put plus 0 to signify that. Equals, what energy do I end with? Am I moving? Yep, there's kinetic. Am I above ground? Am I above 0? Where do we want to put 0 in this problem? Where's convenient? Let's call the ground 0. You do not have to make the ground 0. In fact, you can make 0 where the ball ends up. You can make 0 where the ball starts. 0 is convenient, the ground here, because I tell you how high the ledge is with respect to that and whatever. But you get to decide. Yes, I am above the ground at the end. In fact, that's what I'm solving for. Y final equals question mark. The mass cancels out. And it's such an easy, mathematically, a very easy problem to solve. The alternative is doing a kinematics problem where you find the time of flight, and they use that to find the velocity in the y direction. And then you thankfully remember, oh goodness, let's see, how high is the ball going? No, it's even worse than that. Let's see, what would we do for this one? We have the final velocity, we have the initial velocity in the y direction. So maybe it wouldn't be too bad. You could look at what equation, I think it'd be VF squared equals V naught squared plus 2A delta Y. That would let you do it. Fun fact, if you rearrange this equation, it turns into the other one. If you don't believe me. So I just told you all that VF squared, remember this is an equation from kinematics. Just want to show you all something real quick. This equation here, so we have 1/2 V initial squared plus G times Y initial equals 1/2 V final squared plus G times Y final. I'm going to group my velocity terms together just to show you all something nifty about this. You know what? Let's just do it. Let's just multiply everything by 2. Maybe that won't be as obvious. 1/2 V final squared equals 1/2 V initial squared. Though that is getting, no, that's fine. Plus G. That's kind of interesting here. We get Y initial minus Y final. If I multiply this by everything by 2, this goes away, and this gets a 2 in front of it. And look at that. You all got the same expression from kinematics. We derived the kinematics expression. Vf squared equals V initial squared plus 2G. And you may be very confused here. Why is Y initial minus Y final? It's because when we plug in G into energy, we put it as a positive. When you do it in kinematics, you put a negative and it'll flip things and make it correct for you. So, ta-da! Look, they both work. It's kind of satisfying. All right, let's actually do some, so now we'll just do some example problems. We got some time. I think, how many problems do I have? 4 maybe? Ooh, 5, how exciting. All right. A horizontal spring is located 5 meters above the ground. If I compress a 10 kilogram box on the spring 0.5 meters and the spring constant of 1,000 newtons per meter, how fast will the object go right before it hit the ground? Assume no air resistance. Draw a picture. Draw a picture. What kind of problem is this? Go from there. I'll give you all a few moments. Yeah. Yeah, so why was the great question? Work here corresponds to anything that's not explained by velocity, gravity, or springs. So in this problem, we don't have anything else affecting it. We don't have any air resistance. We don't have any friction. We don't have any push or pull. And so work is 0, therefore. Work is basically anything not accounted for by gravity or springs. Yep. Draw a picture. If your picture's bad, your problem's going to be bad. And based on my studio class, I did see some people draw this wrong. It's always going to happen. And then everything else goes bad. So that's why draw a picture. If you can't visualize a physics problem, you're going to have a heck of a time solving it. All right, so I got a spring above ground. It is a horizontal spring. If you drew that spring vertical, it ain't going to go well for you. It's located 5 meters above the ground. If I compress it 0.5 meters, how fast will it go right before hitting the ground? So that's my initial. My final is the box right before it hits the ground. Obviously, after it hits the ground, it's 0, but that's a whole other problem in itself. So I'm going to kind of immediately jump to step 3. We could write our givens and all that jazz, but for the sake of time, what type of problem? Okay, look, it tells you what type of problem it is in the title, which is a little disappointing. It's conservation of energy. Energy initial plus work equals energy final. What energy do I start with? Is it moving in the beginning? Nope, no kinetic. Is it above? Where do you all want 0 to be? Let's do ground. Is it above ground? Yep, so it's got mgy initial. Is there a spring involved? Yep, 1/2 kx squared. There is a spring compressed. Is there any air resistance, friction, or anything else pushing or pulling this object? Nope, no work in this problem. All right, at the end, there's only one type of energy I have. What is it? Kinetic. And if you solve this problem, we'll solve it out. Notice mass does not cancel because the spring equation doesn't have mass in it. So don't cancel mass. So we get that V final equals 2 times all that nonsense. Normally I like to rearrange it, but for the sake of I'll just put the numbers in. I'm going to have to do it anyway. V final equals the square root of 2 times mgy initial plus 1/2 kx squared divided by the mass. This is how I do problems. I solve for the variable I want in terms of the variable I need, and then I plug it in, because the beauty of this is I only have to do one enter on my calculator. The longer you leave things in variables, the easier it is to check your work as well. If you haven't realized, once you start putting in numbers, you kind of lose track of what numbers where. They start to get combined, they start to get moved around, and it gets really tricky to follow if you're doing the math right. When you leave things in variable, I can actually check my work. So this term is right here, good, I multiplied by 2, I divided by m, and then I square rooted it. It's easier for me to follow the math logic I did when it stays in variable form. You're going to see me do that today. Normally I don't do that because it confuses people. But at this point, we've been doing these problems enough that I don't feel as bad. This is how I solve problems. And as you do more and more, you may or may not do the same thing. And so I get to plug one thing in my calculator and hit enter, and I get an answer, and then I only have to check one equation to that equation to make certain I put the right numbers in the right spot. It reduces error. And I get 11.09. And I ask myself, we do not want to forget to ask ourselves the very important question, does this number seem reasonable? Does this answer make sense? So we look at this problem, we say it's dropping 5 meters. That's pretty far. Like 5 meters, that's taller than the ceiling is above me by like an extra couple meters. So that's a pretty good height. So you're going to get a lot of velocity from falling. Plus you got a spring that's pretty strong. 1,000 newtons per meter literally means if I compress this 1 meter, it pushes with 1,000 newtons. That's what that expression, every meter that you push this, you get an extra 1,000 newtons of force. So yeah, that seems reasonable. It's not a crazy high number, but it is fast. 27 meters per second is 60 miles per hour. This is about 25-ish meters. So about 25 miles per hour. Fast, but not crazy so. We're good. Do ask yourself those questions. Does it make sense? The more things you can do to check your work, the less likely you are to make a mistake, and you're going to make a lot of mistakes in life. It's going to happen. All right. The next problem is the exact same problem. But now I'm asking how much work was done by friction or air resistance if the final velocity is 2 meters per second. Try to build that one, y'all. I'm going to copy and paste the picture over. It's the exact same picture, so this will save me some time. Exact same picture. So bread and butter, energy initial plus work equals energy final. In this problem, though, we're solving for work, so we could rearrange that now if we wanted to. And remember, this is actually how it's going to be shown in your equation sheet, is work equals change in energy. So I'm just acknowledging that now. I'll give you a few more moments to set up that equation. The answer is a few hundred joules. I forget how much, like 500 or something. I'll solve it in a second to get the exact answer. So yeah, you just ask yourself, what energy do I end with? What energy do I start with? It's the exact same as last problem. What energy do I end with? Kinetic. That's the only energy I have at the end. What energy do I start with? Spring and potential. Exact same as the last problem. Just now we're actually solving for work. Last time the work was 0. So you plug in the things. Yeah, there's no real way for me to simplify this any further. It's solved for what I want it to be. The mass is 10 times the velocity squared, so 2 squared minus 1/2 times 1,000 times 0.5 squared plus 10 times 9.8 times 5. And then I guess you just put that in my calculator in one big lump. Yeah, hey, my memory wasn't terrible. Negative 595 joules. The negative comes from the math. And again, we ask ourselves, does that make sense? Well, first we look at the negative sign. Is that reasonable? Should it be negative or positive? Does friction / air resistance take away energy or add energy? So it's negative. Always takes away. And then whether or not the value is reasonable, joules is kind of one of those I don't really give it a benchmark on. So it's kind of hard for us to say how much energy that is, but it's really easy for us to get a benchmark of energy. Benchmark of energy, let's take a 1 kilogram mass 1 meter above the ground, and gravity is 9.8. So if you want to find a benchmark for how much energy something has, how much energy does a 1 kilogram object have 1 meter above the ground? 1 kilogram object times 9.8 times 1. 9.8 joules is the energy a 1 kilogram object has 1 meter above the ground. If I drop it, that's how much energy gets changed to kinetic energy. So, looking at this number, we're like, that's a really big number compared to that energy. But yeah, if you all remember the last problem, instead of going 11 meters per second, this thing's only going 2 meters per second. It lost a lot of energy. It lost a lot of energy. So it went from going like over 20 miles per hour to going 5 miles per hour. It's real slow. And 10 kilograms is a lot. Like that's 22 pounds. It's not a small object, relatively, depending. All right, great. A 5 kilogram rock is sitting still. Suddenly it blows up into 2 pieces, one of which is 30 kilograms and has a velocity vector of 3I minus 7J. What's the velocity vector of the other piece? Try it out. Draw a picture. Set it up. Let's see. We got this one. I think the next one is the same. No, it's a different one. So I'll just give you at least time to decide what type of problem this is, and then I'll quickly go through it. There's my rock. Here's my 2 pieces. One's going to go to the right and down. So maybe one goes that way. The other one you can guess. A picture will help you also check your answer. You can probably guess if one piece goes down to the right, the other's going to go up to the left. Like you all have seen things blow up. That's how things kind of do because of conservation momentum. So these kind of things are very helpful. And maybe a bit more that way. So therefore, maybe a bit more that way. All right. So it's going to be conservation momentum. Again, I'm going to kind of whip through this because we got a couple more I just want to show you. So, this is a conservation momentum. So my momentum initial equals my momentum final. What's my momentum initial? 0. Rock ain't moving. Initial momentum is 0. What is my final momentum? We have mass 1 times velocity 1 final plus mass 2 times velocity 2 final. We're going to put little vector hats over these. And I've actually seen people using this notation. I actually like how they were writing it. People were putting the vectors in the math, which I think is actually kind of nice. So I'm actually going to do this one that way. So we're going to have 0 equals mass 1, which is 30 kilograms, times, and I'm actually just going to put the vector in here. I think this is nice, as long as you realize you should never subtract 3 from 7 or 7 from 3. You got to keep them separated. But you can do x and y components in one equation as long as you're careful and you don't mix and match your j's and i's. So there you go. We just kind of chuck it all in. And then we're solving for V2F. So V2F, the vector, is going to be 30 times 3i minus 7j hat all over 20. Oh, and if you're wondering where I got the 20 from, 50 minus 30 is 20. That's something you have to kind of make that step. You got two pieces. They have to add up to the original. Otherwise, I vaporized some rock. And we're going to assume no rock was vaporized. You can't do it if you have that. So anywho, we get, you just do some math here, keeping your stuff separated. So I get 90 over 20. I'll just plug it in. That's fun. 90 over 20 I hat minus 210 over 20 j hat. I just transferred it in, kept things separated. And you get 4.5 I hat minus 10.5 j hat. So, what's nice is you can do x and y components all together if you're just careful. It is kind of convenient. Yeah. Ooh, thank you. See? If you rush through things, you do something stupid like I did. Where did the stupid happen? Right here. And if I had done step 5, let's see if my answer makes sense. Let's actually check this. How would I have identified that this is the wrong answer on the test? I get this and I say my math looks good. I look at my picture. Which way should that thing be moving? We said logically, if object 1 is going down to the right, object 2 needs to be going up to the left. Look at this answer. This answer says I'm going up. This answer says that object 2 is going the same way as object 1, which is nonsense. So, that is a way you can check to make certain you don't mess this up. If you draw a picture, it lets you check these things. So this is wrong. I forgot to put a negative sign in front of this whole thing. Why is there a negative sign? Because I was supposed to subtract this to the other side. That kicks a negative. Then you divide the 20. So yes, this should be a negative 4.5 plus a positive 10.5. And I also was a little silly. I forgot to put a unit. If you don't put a unit, you're a chump. I was a chump. All right, and let's check this one. Hey, it's negative 4.5. That's the left. Yay. 10.5. That's up. Yay. It matches my picture. That's good. So, anything you can do to check your work is useful. Yeah. Yeah, it's a good question. The question is if they had the same mass, should it be the same velocity vector? Yeah, but opposite. Yep, exactly right. If it has more mass, the velocity just ends up being less correspondingly because equal forces, and if you have more mass, you experience less acceleration, so it all connects to Newton's third law as well and Newton's second law. All right, next one. 500 kilogram car is traveling 30 meters per second and runs into a wall. How does the force of a person compare to time of collision? 0.5 seconds compared to 2.5 seconds. I'll give you all a minute or so to see if you can figure out what strat you're going to use for this. What type of problem is this? There we go. There's my picture. So, if you ever see a collision, you should think momentum. And this one's going to kind of trick you because you're like, how do I do conservation of momentum for this? So this is where you have to remember that it's not just P initial equals P final. It's technically P initial plus the impulse equals P final, or more specifically, the way you all see this in the formula sheet, change in momentum equals this. Change in momentum equals the force times the change in time. It's just like energy. The change in energy equals the work. So if my energy changes, work is being done. If my momentum changes, a force is acting on it. It's a nice little kind of connection there. If my energy is changing, something must be adding energy to the system or taking away. If my momentum is changing, a force must be acting on it. And this is the relationship between those. So, kind of nice to know that. To that end, if you notice here, the initial velocity and the final, so initial velocity is a number, final velocity. Initial velocity is 30. Final velocity is 0. And then the time, we have time 1 equals 0.5 seconds. We have time 2 equals 2.5 seconds. If you notice, when we get to how do the forces compare, force 1 equals question mark, force 2 equals question mark, woohoo. When we get to this equation, delta P equals change in F times change in T. Their change in momentum is identical. Remember, we did this. This is the one that like really people did this one a while back and people didn't like it. How do the forces compare? The change in momentum is identical. They are both going from 30 to 0. The only thing that's changing is the time. So if we have like delta P1 equals F1 T1 and delta P2 equals F2 change in time 2, the change in momentums are the same. These are the exact same value. They're equal to each other. So if that's the case, we get that F1 times the time equals F2 times the time. And then I'm not gonna try to cram the rest of this in the corner. So we'll pull that on over. And then the rest of this is very straightforward. We're just gonna put in things. So step 4, so we find that the force of 1 times 0.5 equals the force of 2 times 2.5. And if you rearrange that, you get the force of 1 equals 5 times the force of 2. And we check. Does that make sense? Does it make sense that the force is greater in the first case than the second? If I slow down in 0.5 seconds, yeah, I need a bigger force than if I slow down in 2.5 seconds. I am slowing down. My change in velocity is the same. And you will find something that's kind of nifty that if you haven't realized, this expression here, let me just write this out a little bit. M times change in V equals F times T. Divide the mass to the other side. You get change in V. F over M is A. It's the kinematics equation. Yeah, it was there all along. The change in velocity is acceleration times time. Yeah, so it's kind of nice to see that it's the same thing. It's just another paint job on it. And it makes sense. If my change in velocity is the same, I need a higher acceleration for it to happen in less time. Great. All right. Last one, which is center of mass. And I'll post these slides. I know I'm kind of whipping through these, and you don't really have time to write down what I'm writing, but I'll upload these, so all the writing will be there. All right, coordinate system. Draw a picture. A 3 kilogram object is at 3i minus 2j. Where should I put a 4 kilogram object so that the center mass is located at 2.5i minus 7j? What I really would like for y'all to spend a minute doing is draw where the heck these objects should be. Where is object 1? Where is the center of mass? And then predict where object 2 should be. Just based purely on the picture. So object 1 is located at 3i minus 2j. That's 3 to the right, and that's 2 down. So let's just call that right there. Let's call that object 1, because I don't want, or 3 kilogram object. Center of mass is located at 2.5i minus 7j. That's 2.5 over, that's 7 down. So that's a little bit less over, but way down here. And we're going to call that the center of mass. And you can hopefully predict where object 2 is going to be. If object 1's up here, and the center of mass between it and the other object is down here, object 2 is going to be somewhere way down here. This is useful. It lets us check our work. If you get an answer where the y-coordinate is positive, you're wrong. If you get an x-coordinate that's to the right of the center of mass, you're wrong. So real quick, just to kind of set this up so you can have the answer, but I'll post these. So remember, our center mass equals 1 over the sum of the masses times MI/RI. So we get 1 over mass 1 plus mass 2 times M1 times the vector R1 plus M2 times the vector R2. And all of this equals the vector, which is the center of mass. Again, I really like how I saw someone else do this today, where they did this in vector notation. So you just put the vector notation for center of mass. So 2.5 I hat minus 7 j hat equals 1 over mass 1 plus mass 2. That's going to be just 7. Times 3 times the vector notation for that. 3 I hat minus 2 j hat. Plus 4 times the vector for 2. And then what can we do here? We can just simplify 2.5 I hat minus 7 j hat equals 3 times 3 is 9. So I get 9 over 7 I hat minus 6 over 7. Ooh, don't do that. That's a terrible idea. Multiply the 7 to the other side. 9 I hat minus 6 j hat plus 4 R2. And you can go through all the math, and we're at 2 minutes left. I guess I can just do it real quick. I'll put the answer up here. 7 times 2.5 minus 9 divided by 4. Sorry, that all accidentally. We get that R2 equals 2.125 I hat. And 7 times negative 7 plus 6 divided by 4 minus 10.75 j hat, which makes sense. It is to the right. It is 2.125 is smaller than 2.5. Yay. And negative 10 is down here somewhere. Yay. So you can try that out for yourself. It's a good extra practice or whatever. But there you go. Have fun. Good luck. No classes on Monday. Not that it matters for us. Oh, that means I don't have office hours on Monday because there's no I'll have office hours tomorrow from like 11 to 12. I'll send an announcement. I'll make up for it by having them tomorrow. What's up? And I got you next.
Okay. I know that for the E plus W because the energy final.
Yep.
I want to test why gravity doesn't work for that. So I know for a lot of websites, I also saw that they write it as W not considered.
Yep. So energy, we have an equation